And m basically quantifies how much defect is in the mass flow of the boundary layer, which is related to what thickness of the boundary layer? The displacement thickness, right? Somebody remember what is the displacement thickness?
Integral 1 minus
Integral 1 minus
small u over
small u over big
big U.
U. Right, in this case, let me just say I'm using my UI. All right. dy, this is an integral from 0 to infinity, right? This works very well with our defect. In fact, if I multiply both sides by what? I can get the defect.
Yeah.
Yes, if I multiply ui on both, so basically ui at y equal to 0, right? So ui at y equal to 0, y equal to 0, then I can cancel these two, and this is my m. All right. Make sense? So here, the dm dx can be considered as dui. Okay, so let me use ue instead, because that's a lot more closer to the convention we had last lecture. So this is because m is equal to ue times delta star. This is due dx times delta star plus ue times d delta star dx. So this is equal to vi. All right. So if you so that is going to give me a relationship between the increase in the displacement thickness of the boundary layer to the wall normal component of the inviscous effective fluid. Okay, so if the viscous fluid goes out of the boundary, you have a growth in the displacement thickness. If Vi goes into the boundary, into the wall, then your boundary layer thickens. If Vi goes out, your boundary layer thickens. This is also somehow intuitive if you consider what is the definition of the displacement thickness. Right, so for example, it's easy to think when you consider a constant UE. Then what we are saying is that d theta star dx is equal to Vi divided by UE. All right, d theta dx, in some sense, is the angle or the tangent of the angle of the inviscid equivalent fluid at the wall. So you have a boundary layer that grows like that. This is the wall. The boundary layer grows like that. And your inviscid equivalent flow goes out of the boundary layer in such an angle that is Vi and UE, right? So Vi over UE in this case is actually the angle at which the displacement thickness grows. Instantaneously, right, exactly. So the inviscid equivalent flow at the wall is tangential or parallel to the like outline of the boundary layer defined by delta star, right? So this is a very intuitive equation. So these two are going to be very useful. And these two are going to be useful later. Okay, so this is the first equation we derived that basically anchors the y velocity of the inviscid equivalent flow. Any questions so far?
Are they different?
Huh?
The two box equations are they?
No, they are the same. One is just relating back to the displacement thickness of the boundary layer. Right, so m may not be something familiar, but coming to here, we are writing everything into familiar terms.